Hi, Robin here. Going to look at computational methods. This is for the OCR A-Level Computer Science. We're going to be looking at different techniques, and one of the big techniques that we'll be looking at is really the way that algorithms are formed and the kind of aspects around them. And really, with any algorithm, there are certain constraints we must have. The algorithm should and must always come to an end. Again, it should have sort of conditions that cause that to happen. One of the aspects that you can have with algorithm, for example, is like a loop. And if that loop just looped forever, we'd obviously have a problem. With an algorithm, we can also look at how well that algorithm performs, how much memory it takes up, all sorts of different aspects about that. And it's something that we look at within Big O notation. So Big O notation is the kind of the assessment, if you like, of an algorithm. I have done a separate video on that though, so I won't talk about it much now, but it's something that you should be aware of and kind of factor in the efficiency of an algorithm as you're using it. With problems, what we want to be able to do is to apply whatever situation we're in. And therefore, we may use what's called low-dimensional data. And that data is helping us to solve the problem. And again, it's where there isn't that many sort of aspects to that sort of outcome. So, for example, if we're just plotting a simple course from A to B, there isn't too many variables, too many different constraints on that. In contrast, if we have high dimensional data, this would be where that's going to cause us loads and loads of problems because of all of the different dynamics to that data. A simple example of this would be like a weather chart where how often our sort of weather prediction's inaccurate. Well, it's all the time, isn't it, really? And it's very, very difficult with the weather, say, to predict an exact, precise moment as well. At 2 o'clock in London, in the centre above Buckingham Palace, it is definitely going to rain. That accuracy is almost impossible because of all those different factors that's going to cause that. And therefore, it's more of a general area. Yes, it'll rain over London at that particular time, can be said with much more confidence. And that's something we just need to think about and to factor into the decisions that we're making and how we process that. Other aspects that would suffer with high dimensional data would be something like a stock market. Again, if we could all sort of master predicting the stock market, we'd all be millionaires. But unfortunately, there's loads of different dynamics out there to what can cause a stock market to increase in its value or decrease. As simple as a comment that's made by a president in an interview on the news or something can have an impact on the way that stock market changes. And that's obviously incredibly difficult to predict and to factor in. When we're looking to define a problem, we should look at the initial situation. We should make sure we're really clear in our mind about the goal that we're trying to achieve. And really, we want to make sure that there's somebody checking, does this actually do what it's supposed to do? And again, that will then help you to understand what's going on and the way that it kind of is carried out. One aspect in which we can use to try and solve a problem is enumeration. This is where we're trying to just use an exhaustive approach to just try every single possible aspect that you can have. A simple aspect to this would be a brute force attack. That's when you're trying to hack into somebody's account, and you just try every single possible password you can possibly think of. And eventually, if you guess enough, you should theoretically get in. And obviously that is a process that we want to either be aware of that somebody could try and attack our system with and therefore try and come up with constraints to prevent, or we can just use this to know that eventually we should always get to the answer. However, it could take us an incredible amount of time. Trial and error is very, very similar to enumeration. The only real difference here is that by trialling something, looking at what went wrong and then trying to improve on that, we should then hopefully end up with a better outcome. So whereas before we were just trying every random password we could think of, now we're actually trying to think, I tried that certain letter, I think that first letter was correct, I'm going to keep that and and try the second letter and change that instead. And it should hopefully improve our accuracy and our speed in solving that problem. Another method we can do is performance model. I've already mentioned Big O notation already, but with Big O notation, we're basically saying, okay, in this scenario, this particular algorithm is going to have this particular cost. And therefore, we can sort of analyse whether that approach is the best approach in that particular circumstance. Performance modelling is also really important in things like networks, where you're looking at how data is passing between two nodes, and therefore kind of can weigh up if there's a problem and if there's some sort of solution that needs to therefore be put in place to solve it. We can also use simulation. Simulation is incredibly powerful because you can therefore predict how, say, an event is going to carry out. And again, in my simple example here, I've got a wing from an F1 car, and you can see how the air is moving across that. This can therefore be done on a computer. And if you think about that, that's going to save us loads of money and time and effort, manufacturing costs, etc. The cost of the actual materials to make the wing. We could do that all on a computer, simulate what we think should happen, and then once we're confident with it, we can then actually build that, say, front wing in this case, for real, and it should then have the sort of performance advantages that we were hoping to achieve from it. Another aspects of simulation is things like making predictions on things, so we can simulate the weather, we can simulate sort of other modes of transport. So for example, a lot of pilots will train on a flight simulator before they ever actually get into a real plane, and therefore they can build confidence in the dials, in the systems, in the process. And obviously you're much better to crash a flight simulator than you are to crash a real plane, aren't you? So we want to kind of factor in those sort of aspects with simulation and really get those benefits of it, but to be able to mimic real life as closely and accurately as possible. We can apply a theoretical approach. In many ways, theoretical approaches are the methods used by science, aren't they, in many ways? Something like the Big Bang theory or string theory are both theories at the moment. They've not been proved yet, but by having that theory in place, you can start to build evidence that supports it and really gain trust in that particular theory, and therefore rely on that and be like, yeah, we're pretty confident this is the case, this is true. And then you can build other judgments based off that. So if that particular theory we deem it to be true, well, what other theories can we then create from that that could be used? What all of this should lead us to is creative solutions and just trying to think sort of outside the box, thinking about how you can approach that thing, how you can sort of work around it. And again, it has benefits and disadvantages to this. In many ways, a creative solution can be the massive turning point in sort of the solving of a problem. However, if you get that wrong, that can be incredibly costly. And again, working through different solutions, if it's something completely different to the things you've done before, you've then got to work through the various issues that may come from that. Okay, another method would be problem decomposition. As you can see here, we've got a module chart. Each of these columns represents a separate module. So you can see we've got a functions module, a user module, product module, and a payment module. And what this does, it helps you to break down a big problem into more manageable chunks. In other words, each of these squares would therefore represent a sub-procedure effectively that you would need to carry out. So you can see in the user column, we've got sign in and sign up, and therefore the sign in would be a process we would just need to manage. And we could do that in isolation of the other aspects. It just helps us to organise ourselves, helps us to break that problem down into a more manageable chunk. Another approach is divide and conquer. This is used many times within algorithms, particularly quicksort, merge sort, and binary search, all use a divide and conquer approach. In other words, what you're trying to do is take the big data set, split it if you possibly can, and then use the smaller data set to then approach, again, a repetition of that splitting. What that should mean is you are improving the circumstance every time, and certainly a binary search is a really quick method to find data by using this technique, and sort of really focuses in on the area of the data that you really need to find. Really quite powerful technique. Again, you can sort of see here with the binary search that we start off with our longer list. We're looking for R in this case, we compare it with M. R is greater than M, so therefore we split the list, as you can see there on the second one. We then look again. T is our middle point here again, so in this case R is less than that, so we split that again. We end up with another small list again. P is now our midpoint, R is greater than P, again, we can split it again, and then finally we find R in the middle there, and we know that we've found the data we were looking for. Visualization is an incredibly powerful technique. I've used visualization in this video, haven't I? To demonstrate things, to show things. Really kind of gets that mental image going, really helps you to understand sort of what's happening in a much clearer and easier way, I always feel. And I know personally, once I've sort of visualized something in my mind, it really helps my sort of memory and to kind of remember whatever aspect it is that we're using and working with. And I know a lot of students find that as well. So, for example, here we've got a binary search. It's using a binary search tree. Again, if we're looking for the letter R, we would start with the M side. Because we know that R is greater than M, we can discard that entire half of the tree. Again, now we're comparing it with T. R is less than T, and therefore we can again discard that half. Now we're comparing it with P. It's greater than P. Again, we can now discard that half, and now we've found the item we're looking for. So that visual aspect is exactly the same as the binary search that I showed you with the list. It's just in a more visual way of seeing that, and again, helps with that understanding, helps you to see what's going on. Again, graphs are a really good example of visualization. Here we've got a linear search demonstrated. Again, it's proportional and therefore goes up in that diagonal straight line. And again, once you've sort of compared various graphs, it really helps you to understand them and to make judgments between different outcomes. I'd certainly recommend that you try and draw graphs for different searches, different sorting algorithms. They'll really help you understand the differences between them and the different impacts that the algorithm's having on speed and on sort of memory and space and all those different factors. Again, we can sort of represent data like this. This is an adjacency matrix. Opportunity for you to pause the video here and see if you can draw the weighted directional graph from this, and also can you convert that into an adjacency list as well. So like I say, pause now and then I'm going to show you the answer in a moment. Okay, so let's have a look at the answer. You should have got that. You can see that the adjacency list is here, and again we've got the graph shown. Notice the brackets on the adjacency list. This is because this is directed. It therefore has those curly brackets. Just be aware of that. It can differ with different types of graph. Okay, again, we can sort of demonstrate backtracking visually. So here you can see that we're going to use this particular tree, and you can see we're starting with A, and we're going to go through this tree, and we've worked our way down to D. What you can see therefore is we need to backtrack. We've exhausted all of the possible routes we can take. This is a depth first traversal that we're carrying out here, isn't it? And therefore we need to backtrack. We go back to B in that regard. We're looking to see if there's any other nodes to take. There is, and therefore we would take E. Again, we've reached a dead end, so now we need to backtrack. So we're going to go E, B, A, and then we go down the other side. We're going to keep that process going. So C and then F. Then we'll go back to C, then we go to G, and then to H, and then back to G, and then to I. Once we've reached I, we still need to backtrack to confirm there are no other existing nodes to take, and therefore we're going to go back all the way to A, and we've now completed it. This same process is really useful for, say, solving things like a maze. We could carry out, again, a depth first traversal here, and therefore we can find the correct route to Z. If we're going to do so, we'd start at A, we would go all the way down to D, you sort of see we're following that maze through. This would go into a stack, and it's worth noticing that, and again, this is why that behaviour happens, because obviously we need to pop those items from the stack. So we're going to pop D from the stack, we're going to add E, we're going to pop E from the stack, we're going to pop B from the stack, and we're going to go back to A. Notice A remains in the stack. We're then going to add C and F, as we've done here. We're going to pop F, and we're going to then have G and then H being added. We're then going to do the same, where we're going to add I and J. We're going to need to pop J, and we're going to add K, and then Z, and then we've actually found the route that we can go through to get there. And we know, therefore, that the route is A, C, G, I, K, Z, and that will find our way to the exit of that maze. We can use the same process within Dijkstra's algorithm. So with Dijkstra's algorithm, we want to find the shortest path. So with our graph, we want to look at the different routes between each node. So we can start at A, we're trying to get to E. So with A, we would visit it, and we want to check where are all the places I can get to from A. So B at a cost of 3, C at a cost of 5, D at a cost of 2. And again, we would continue with this. I have done a much longer video on Dijkstra, so I won't spend too long explaining this now. But ultimately, what we're trying to do is look for the next shortest route, so therefore in this case D, and again, where can I get to from D? Again, as we move through to B, We can add on update it with the roots that we've got. Again, C, and then finally E. And what we end up with then is from A to C is that root of E, C, B, and then A. In other words, A, B, C, E is the correct route through that. Okay then, as you can see there. Another possible route for sort of solving a problem is data mining. And therefore what we're looking here to do is to find patterns and trends within data. This is commonly used in all sorts of different fields. Say it might be to make predictions about something. I use this in a teaching capacity to look at assessments and look at the trends of an assessment and how that's performing. Again, we can do this for sort of all sorts of things, like use it for cybersecurity, use it for fraud detection within banks. So a bank, for example, will look at your usual spending patterns, and if there's a sudden change to that, they could suspect that there's some issue, something going on there that shouldn't be, perhaps. Again, we can use it for recommending products from a point of view of, say, Amazon or Spotify would do so. A really useful and powerful technique to use. I've already mentioned some fraud detection there, but again, kind of sort of offering us that sort of ability to do something. Again, a little moral dilemma. I think it's worth thinking about this from a 9-marker point of view or a 12-marker point of view, about how fraud detection is effectively looking at your spending patterns. And again, you can argue that that is actually intrusive, it's invasive on your privacy. Should somebody be monitoring your spending? Should you not be free to spend your money as you want to? Versus the cost of not doing, and therefore we would lose the ability to spot fraud. You're losing those protections from the bank, and you might as well therefore be keeping your money under the mattress, mightn't you? So again, it's just something to think about. It's something that I would perhaps suggest that you ponder, because again, it just gives you that moral dilemma. You might think about what laws could apply here as well, and the different factors around that. Heuristics, incredibly useful. They're a best guess, ultimately. And again, we can use that to solve different sorts of problems. We can guess somebody's password if we know something about them. We can sort of make final predictions. Like I said, I can use heuristics to guess if students have performed in a certain way previously, how would I expect them then to perform in the final exam? And again, we can use heuristics for all sorts of other things, so checking for viruses, for analysing data in some way. Artificial intelligence can use heuristics to, again, approach sort of solutions to answers. Another use of heuristics would be in an A-star algorithm. So again, do you know how to do this? Pause now, and you can sort of test yourself and see if you can, and before I give you the answer. Okay, let's have a look then. So with the A-star algorithm, we want to set it up really like Dijkstra's algorithm, and the first thing I would always recommend you do is in the heuristic column, just fill in all of the heuristics. So in this case, the red numbers on top of each node. Once you've done that, really you're just following Dijkstra's algorithm once more again. So again, we're going to start with A. We're going to fill in all the nodes you can get to from A, so that'd be C, D, and B. We then continue with D, the nodes you can get to from there. We then look at C, B, E, G, and F. And then to get from A to G, the shortest path is actually from A, D, G. You can see from that. I have got a video where I've explained this in way more detail and sort of with a lot more explanation of it. So I do recommend you go and look at that. With that, I just wanted to show that it does use the heuristics as we're going through. And again, in this case, the heuristics is giving us a guideline on the best route to take. And it could be representing all sorts of things like, say, traffic on the road, or a particular sort of cost of, say, petrol or money, or whatever it might be that might give us that indicator of a real-life situation. Okay, pipelining, again, is another process that we can take into account, and the sort of the usage for that. Again, it's sort of the processor itself should be something we can consider, whether we're using parallel processing or concurrent processing, how that pipelining is happening. Is it happening sort of simultaneously, or is it sort of being interrupted by lots of branches, which would cause us to then need to flush the pipe as a result of that. So again, with this, it's something we can factor in that can then aid efficiency, aid the performance of that algorithm. If you're not so sure of some of the things I mentioned there, such as concurrent processing or parallel processing, I have got a separate video on those, which again I would recommend you watch. I'll put the links to that. Okay then, so I hope you've enjoyed watching that. I hope you found it useful. Please do like and subscribe. Help me to help others. Really do appreciate it. And hopefully see you again. Thank you. Bye.